So as I said,
Okay, you can start. Good.
yeah. All right. So as I said, my background, working in Shell in research, took a sabbatical, pursued a PhD on CO2 EOR um, from University of Texas at Austin. Came back to the industry, implemented some of the EOR models that I developed for Middle Eastern reservoirs, actually with high salinity. So the problem we were solving was essentially seeing how CO2 injection impacts the geochemical reactions associated with high salinity reservoirs, which is what is present in the Middle East. Uh, and then I moved to academia for a while. I was a postdoc in Princeton, and then I was a postdoc again in computational sciences in Austin. And in 2017, a few of us who had essentially experience of working in industry, working in academia, saw that these tracks were not necessarily moving in the same direction. So you had the academic track where you're trying to build these next generation models, but essentially the industry side, where the focus was more about trying to use models which can enable decision making, right? So we saw this opportunity to merge together. Cloud computing was happening during that time. Browser-based models were, making some kind of a surge, and so that's how we set out building Reservoir. Um, we were awarded the most promising startup at Offshore Technology Conference in 2018, and since then, essentially, we pushed forth. That's given some recognition, and we pushed forth some models, and we have a product in the space. And what I want to talk about today is essentially some background around how we are combining these specific models, how we are using these models, and also touch upon some applications in water flood injection applications. Um, a lot of stuff that I shall talk about are mostly for conventional reservoirs, but I shall also explain how they are typically extended onto unconventional, because I know in North Dakota, the area that you guys operate, typically you have a lot more unconventional reservoirs there, right? And also, yeah, I shall touch upon water flood, but also these are readily extendable to gas injection, whether it is half and puff or the other types of gas injection that you may have. Yeah. So with that being said, so here's an agenda for my talk. Is start with the motivation, why we do what we do, essentially, how we why we focus on conventional, and through that extend it later to unconventional. Um, I shall give a background of some models. When I speak about different models, what do I mean by them? How they are applicable, just to set stage so that we understand what is the difference, what are some of the commonalities between the models, and how best you could combine them in order to drive decision making. Yeah. And then I shall also touch upon a couple of applications. One I shall do for water flood. This was a field in Germany that we worked on. Uh, and I shall also then touch upon some new reservoir management workflows that we have or that we're working on actively, and how that is actively reducing um, essentially decision making times. Yeah. And then I shall finally draw upon conclusion. So hopefully, towards the end of the talk, you would be able to see how hybrid models really can really help reduce the decision making times associated with both greenfield. What I mean by greenfield, especially for those of you who don't know, would be a field where you never have had any active drilling. It's just an acreage. And you're trying to essentially drill your first wells in that acreage. So those are greenfield. And brownfield, where you've already operating them, perhaps you are trying to do another infill well out there, or perhaps you're trying to do some kind of a enhanced oil recovery operation in those fields. So I shall talk about how these hybrid models can really help you reduce both greenfield and brownfield decision making times. All right. So let's start with the motivation. So as you we obviously, here in the US, we hear a lot about unconventionals, right? I mean, the shale and the parts of it, but when you take a step back and just look at pure numbers, actually 70% of world's oil is coming from conventional mature fields. Yeah. Mm. And I make this comment here because we are also in the midst of a lot of energy debate happening all around us. So it's important to remember where majority source of oil currently is coming from. So it's coming from conventional mature fields. And what you see here is obviously a map of the world, but the numbers there reflect the kind of number of conventional fields that there are distributed all over the world. So you're talking about more than 6,000 fields being operated in more than 2,000 plus companies. A lot of these companies may be state-owned oil companies, probably producing them for their own consumption. So let's look at these numbers. So you see obviously huge deposits here in the Middle East. Russia, um, more than 1,000. Southeast Asia. Here you can see some fields here in Malaysia, and of course you have a lot of fields here in Colombia, that belt. And actually, it turns out you do have quite less fields here in the US. So when you talk about conventional fields, um, it's about 85 of them here active in the United States. And of course, they change hands, and you always have new players, and then there is consolidation in the industry. So in summary, majority of the conventional oil fields are actually outside the US. Um, but the reason they are significant is because 70% of world's oil actually comes from these conventional mature fields. Yeah. So when you talk about these conventional mature fields, so obviously, we all know the life cycle of actually any field for that matter, but more so in the context of conventional fields, where you typically if you think about um, oil production versus time, you have these typical graphs, which I'm sure you have seen in your courses. So you have the steady increase, you have a plateau typical of primary production, right? And then you have a decline. And when you start having a decline in conventional fields, you can, of course, kind of supplement it by injecting water. The idea being that water will sweep the remaining oil out, as well as contribute to the existing pressure in there, right? So that is typically referred to as secondary production, and and then you also have tertiary production meaning that essentially, and when you start doing that, what you observe is you're able to I would say decelerate the decline, right? As demonstrated by here, you see a steady increase because of water injection, and then again a plateau, and then this starts declining as well, right? And then at the end of secondary, and when you start having that decline in secondary injection or secondary production, you can start doing what are called tertiary production. So in tertiary recovery, what one does is one injects steam, gas, or chemicals. So here the objective is not just looking at displacement efficiency. So here you try to impact, especially in case of gas, you are trying to impact um, phase behavior by converting everything into a single phase. So essentially, and then steam has its own way process of doing that, and of course chemicals also, you're trying to reduce the interfacial tensions between the fluids by injection. So those are other methods that are done typically to increase recovery. And here too you observe a deceleration of your decline, a steady increase, you know some kind of a mature bump, and then a decline. So these are typical ways in which all these books address primary, secondary, and tertiary recovery. So when typically mature fields, when I talk about mature fields, they are already in the declining phase, in the end of the primary production, or probably they already have some kind of a water flood in there. Maybe there is some planning around tertiary recovery. So these are the specific fields that I shall speak about in this respect. So, and why are these fields important? Well, it turns out, especially when we are looking at new tools of analytics, machine learning, which operate more on data, because these fields are mature, you have much more data about these fields, which allows you to really apply these models or these advances that there are that can really help you increase recovery. So the question that we found as a startup answering ourselves is, where exactly are some of these tools more applicable, at least on the reservoir engineering side? And it turned out, it is probably more appropriate in the mature conventional fields. And I shall talk about specific tools related to analytics and machine learning, which can help increase oil recovery in this specific space. Yeah. All right, so let's talk about some background tools. Essentially, what I mean by these different kinds of models, just to set a stage here, right? So when we look at reservoir surveillance and management workflows, uh, I do understand University of North Dakota. I was just having a chat with Habib, pretty heavy on drilling, but I'm sure when you take your reservoir engineering courses, you've probably seen some of these models. But it's important to distinguish between these models. What kind of models they are, and they are equally applicable to actually drilling, production, or other kinds of problems that you might be solving. Yeah. Um, so from a surveillance, from a management standpoint, what I mean by analytics are some kind of a statistical method, right? And tools that operate only on data. So essentially, you're just looking at the data and you're trying to establish some relationship or some inferences from that. Yeah. So that is what we refer to as analytics, at least in this context. And are they simple? Well, hell not, right? I mean, they're much more challenging because it's a challenge to identify which data set to run relationships on, right? I mean, you talk about hydraulic fracturing. There are so many elements to hydraulic fracturing, right? I mean, which specific segment do I fracture? How much do I inject? How much of fluid should I inject for fracturing? So there are so many different variables. So if you were to say that, okay, maybe I just have to fracture in this specific region, that doesn't really cut the crust, right? So there are specific challenges associated on which specific data set to run these relationships on. Well, when it comes to machine learning, these are, of course, new age algorithms, but the background remains the same. The background is something referred to as supervised learning. So in supervised learning, what one does is, I have pointed out two different algorithms: random forest and neural network. So you have labeled data essentially. So when I mean by labeled data is, what the inputs are, what the outputs are for those specific input, and you just feed it into some kind of a model. So essentially, if you give it a new input, it would spit out a new output, right? So that's the broad way of thinking about machine learning algorithms. So it's supervised learning because there is an element of training involved. The training being the fact that you're feeding it some labeled data, meaning specific outputs for specific inputs, and you're feeding that into the algorithm. So again, this is again a new method. The community is still learning, especially the oil and gas community is still learning on how to integrate some of these workflows in existing workflows. Then you have something called reduced physics models. So think about the old models which had some relationships in there, or which had some simplified equations that you had analytical solutions from. So those models typically, they do exist in our industry. They exist as Excel sheets all over. And what distinguishes them from these other analytics or machine learning is they have some background equations associated with. So it's maybe a simplified phenomena that you're trying to represent, right, rather than the entire phenomena. And it has some kind of analytical solutions that are coming in from those equations. So these models were also popular before the advent of reservoir simulation. And these models typically, the one of the challenges is they are accepted academically. People love them, uh, but then it's always difficult when it comes to implementing it, especially in field data. Yeah, because there are so many variations in the field data. There needs to be a way to adapt these models, and I should also talk about how we ended up adapting one such reduced physics model for the purpose of water flooding applications. Yeah. And then, of course, there are reservoir simulations. Simulations is something I'm sure you guys have a course on. So these are, physics-based model where you're trying to simulate the flow, right? So in terms of uh, thinking about reservoir simulations, it's a forward model, right? I mean, you're feeding in different aspects. So you're populating the field, the reservoir with different properties, and then you're simulating the flow, which is based on some governing physics. In this case, is Darcy's law, right? So those are the different kinds of models. Just playing based on data uh, would be the analytics, where you're trying to establish a relationship. Machine learning, again, you're feeding an input output, and then you feed in a new input to get a new output, which hopefully relates. And then reduced physics, where you have some simplified background equations and some analytical solutions of those equations, and you're trying to essentially predict based on that. And the last one, of course, is something we are familiar with, where you have reservoir simulation. So what hybrid models are models that kind of combine these different modeling techniques together. So you don't necessarily use one over the other, but you try and combine them. So what I should be talking about is especially combination of analytics and reduced physics model in one of the examples, and then I shall talk about combination of reservoir simulation and machine learning in a different example. So essentially, how do you combine them? Which methods to use that can really impact reservoir surveillance and management. So that's the broad area that I shall be focusing on. All right. So let me just take a couple of examples of what I mean by some of these approaches. So the first approach I want to talk about is the analytics models, right? Where I spoke about the idea of correlating just the data. And here, what I want to focus on is cross correlation analysis. So, as the name suggests, I mean, it's actually inspired by this idea of signal processing, right? So you have two signals, and you're trying to estimate whether those signals are related to each other. So you're trying to infer relationship between any two signals, right? Uh, and that could be any two type of data, right? So I've just given an example of, let's say you have two time series data. What I mean by time series data is any data that is time dependent. So as an example, you could think of X and Y as X being my injection data. So let's say you have several fields. You are injecting water through one well called I1, call it XT. It's dependent on time, right? Because you're injecting water. And then there is YT, which is nothing but say production that you're measuring in from a producer well, right? And that is also dependent on time. So we can call it YT. Let's say you are interested in establishing a relationship or finding out if at all there is a relationship between the injection data that you have, the flow rate injection data that you have with respect to time, and the flow rate production data that you have from the producer with respect to time. So how do I estimate some relation between XT and YT? So it turns out you can do that by using what are called cross correlation analysis. So these are statistical tools. So the way they operate is, as I have given, there are actually two different types of relationship one can estimate. One is called a Pearson's correlation coefficient, and I just given out the expression for that. So the way it's estimated is, so you have xt, which is the injection data, minus mu, which is nothing but the mean of that time series data, y t plus tau, where tau is actually a phase lag that you introduce, and then mu y is the mean of that data, and then sigma n and sigma y, which are actually the standard deviation of time series data, right? And n is really the number of points that you have for comparison. So in summary, let's say you're interested in comparing injection data and production data. What you're doing is for injection data, let's say you're taking the first 10 months of data, month 1 to month 10. For production, you also take month 1 to month 10. But if you introduce a phase lag, which is tau of 1 month, production data, you're comparing month 2 to month 11. So essentially, you're just sliding the time window in that respect. So that's the way of computing, or rather estimating, if two signals are related to each other. So you do that in what is called Pearson's correlation coefficient. You can also do something similar by using something called a Spearman's rank correlation. So what you do is, rather than using the absolute value of essentially flow rate values, you rank them. What I mean by rank is you rank them from lowest to highest, and then you run this relationship on the rank. So this is called Spearman's rank correlation, and you get something similar. And look, folks have used this before in terms of identifying whether injection and production data are related to each other, and through that you can estimate which wells are connected, which wells are not connected, and hence come out with a water injection strategy. And I shall touch upon some of these ideas and how they are implemented in subsequent slides. And we have a few publications in that area too. So in some sense, the idea behind that is, if you have a strong relationship between an injector and the producer, and if that occurs at a lower phase lag, which is at tau equal to 0, what it means is any change that you do in the injection is immediately showing up in the producer, right? So any change that I do is immediately showing up in the producer. It means I will get a strong relationship at a lower phase lag, right? Which means I'm trying to recycle water there. On the other end of the spectrum, if I get a strong relationship at a higher phase lag, which means that any change that I do in my injector is reaching the producer, but it reaches at a much later time, it means there is a relationship, but it takes time to establish a relationship. So that means that those are my more effective injector producer pairs in the system. Yeah, so that's the concept behind using these approaches, and through that you can actually find where the thief zones are in your reservoir and which are your effective injector producer pairs. All right, so that was about analytics. One specific workflow around just using data to try and determine if signals are related, and if they are, at what time lag they are related, and through that estimate whether you're recycling or whether those are your effective injector producer pairs. The other kind of approach is, of course, machine learning approach. Again, you're operating on data purely, and within the machine learning approach, you have something called decision trees. So think of decision trees as a series of questions that you're answering to really segment your data, right? So essentially, when you think of this as your entire data space where you have circles and triangles, what I mean by series of questions is you're drawing these lines to ultimately get to the point where every segment that you have created contains only that particular data type. So for example, this extreme left box contains only the circles, right? The extreme right box contain only the triangles. So essentially you go on till you really sort out a relationship um, between this data, and the series of questions that you ask are typically called features, right, of this decision tree, and they are widely used for classification as well as regression problem. Yeah, what I mean by classification, what I'm representing here is a classification where you're trying to classify, right, into different groups. I said each group has only one type of data, but also regression, where what I mean by regression is it could be a continuous value that you're trying to predict. You can use some kind of a similar approach here. So the concept behind this approach is you ask a series of questions, and those questions effectively lead to an ultimate decision. So that's the random forest model that probably a lot of you are aware of. So in some sense, random forest is actually a collection of such decision trees where each is slightly different from the other. Right. Uh, so these are available as standard packages in Python. All you need to do is just direct data towards it. Um, and the way one does some similar analysis that I mentioned in the previous case is essentially you just feed it. You just take one producer and you assume that all these injectors are related to, are contributing some production to that producer. You run the random forest model, and you estimate something called feature importance of each of these producers, which ultimately signifies how important that injector is to production coming in from this producer, right? So that is a feature importance value that you get, and through that value you can estimate effective and ineffective injector. So again, a separate approach, but operating completely on data, which helps you determine a list of effective and ineffective injector producers. The third kind of approach that I mentioned are called reduced physics model. And as I said, these are uh, the one that I'm showing here on the screen is something called capacitance resistance model. So effectively, look, they were introduced back in the 1940s. Obviously, lack of computers. So the idea was, can I simplify my injection production problem to a more simplistic representation, and through that find ways of optimization? Yeah. So that was the original thought. So what you do in this specific problems are you assume that you have a producer here, let's say QJ, and then you have several injectors. Maybe these are all the injectors that you have in your specific field. And the way this approach works is you assume that any injection that you do through every injector, some fraction of it is being contributing to production coming in from a specific producer. So for example, F4J could be the contribution coming in from I4, which is an injector 4. And maybe that's the fraction that is contributing to production from a QJ. Yeah. So essentially, the idea is when you add up all these Fijs, they have to sum up to less than or equal to 1, right? I mean, all that you're injecting is ultimately either reaching some producer or possibly going in as loss. So hence the aspect that has to be less than or equal to 1. And then if this fraction is very close to 1, it means that everything that you're injecting through the injector is actually possibly going only to that specific producer, right? So what happens is, in this approach, when you write down the equation and when you actually see, what happens is you get like an ordinary differential equation. You have a closed form solution for that ordinary differential equation, and this is the solution. So essentially what you get is QT is nothing but the production coming in from a producer, and you can see it split as a sum of 3 contributions. The first is, of course, the natural decline, right? If you were to not do any injection, what would be the decline coming in from that reservoir? The second is, uh, what is the influence of my injection there, right? So it is not, and hence you see the I into Fij aspect term there, right? And then the third is essentially, what is the influence based on the change in bottom hole pressure. So PWF is really the bottom hole pressure in that respect. So as I said, in these reduced physics model, there is an underlying equation. You have simplistic solution. In this case, that's what I've represented. And each of these terms here means something. So the way these optimizations or this approach works is, how much you're producing, so QT, right? And how much you're injecting, IT. So through that, you estimate what Fij is. So essentially, you reconstruct this as an optimization problem, and you find what's the best fit value for Fij. And once you know these Fijs, essentially which injector producer pairs are related. Because it varies between 0 and 1. Closer to 1 meaning it is highly related to that specific producer, 0 meaning it is not contributing at all to that specific producer. So that's the idea, or that's the goal behind um, these kind of solutions. Now, these models can also be adapted to challenging fields. Typically, when you talk about the formations in North Dakota, where you have multiple layers, essentially multiple layer problems, you can solve it also using this approach. All you do is you just split it up into multiple injectors. So every layer, you assume that you no longer have a single injector injecting in different layers. You assume that there are multiple injectors, and hence you have more variables that you introduce in the system. And through that, you can construct this equation, and through that, you can also solve it to obtain these. So one of the biggest advantages of this approach is it can actually go back and tell you how much is coming in from each layer, and which injection in which specific layer is contributing. And I shall talk about one specific example of an application that we did for a field in California. Yeah. And of course, there is an additional constraint here, because you don't know how much individual layer is producing, because the same producer could be tapping into multiple reservoirs, but all you measure is what is coming out at the surface, right? So your additional constraint is that the sum of each of these layer contribution has to be equal to whatever you're observing at the surface. So essentially, you can construct and modify and adapt this model to also a multi-layer model. You could also similarly do that for steam flood reservoirs as well. Yeah. And, I think I have given a couple of examples here, references here. And, essentially here, what you do is you just assume two-phase flow here and a varying tau factor in order to essentially map this equation. All right. And, and the reason these models, especially a lot of these 1940s kind of models have been constrained so far, as I mentioned, was the fact that they are more academic in nature. When you're solving bigger problems, it becomes a challenge. But it turns out that some advances in numerical modeling, some advances in optimization has actually enabled solving these more complicated problems. So what we've done as a startup is, essentially we've used some of these numerical tools as enablers to solve these more complex problems. So essentially, our expertise is more multivariable optimization. And there are ways to do that. So the one way to do that is you convert a constrained optimization problem to an unconstrained problem. We use something called penalty functions to kind of solve them. And what's really exciting is we have adapted some of these packages from SkyPy, PyGMO. At least for us, we have the TensorFlow, where we have taken some packages from TensorFlow, which really help you solve these large problems. I'm talking about 800 wells producing from 27 layers. So you can imagine the number of unknowns that there are. So essentially, you can solve these large problems by use of some of these advances. And of course, we've done some fine tuning in order to adapt them. Um, and then we also integrate with GPUs to increase speed of solutions of these optimization problems. So essentially, it just orders of magnitude higher in terms of speed and efficiency as well as consistency. Right. So suddenly you're going in from a traditional reservoir simulation approach to a data-driven approach where you are combining these different approaches to identify effective and ineffective pairs, and through that identify new ways of optimizing your reservoir. Right. So those are some of the advances that we've done. I just wanted to showcase some of the open sources packages that are available, which as a student I think you should be excited. We all are actually, because that just opens up the possibility of really mixing and matching it in your current research, if you will. Yeah. All right. So let's talk about a few case studies. So one of them is, of course, this is a field here in Egypt. We had what is called peripheral injection. So this is very common for a lot of these fields in Middle Eastern, and if you look at Southeast Asian reservoirs, typically they have injectors kind of bordering on the periphery, and the idea is that the water is kind of displacing the oil, and you have injectors all over. There were three different layers, and essentially what we did here was also run cross correlation analysis, and through the cross correlation analysis we were able to figure out which specific injectors are actually contributing to the well. So here what you see on your screen is the actual locations, the circles being producers, the triangles being injectors, right? So we were able to showcase, areas of high correlation between just the data, using just the data. We were able to showcase how, two injectors were contributing to producers in block A, whereas one of these injectors was actually contributing to production for wells in all the blocks. So in terms of prioritizing, let's say for maintenance operations, obviously A9A was more critical, right? I mean, because it was contributing to all the blocks. And then, if they had to target any specific well in block B, they didn't have really an injector to do that because, as I said, just three injectors, one of them were contributing all the blocks and the other two were contributing just to block A. So, there was no way of isolating, uh, rather, focusing injection on block B, which had more oil. So this high, correlation analysis helped identify block specific injector contributions. Um, and then we also showcased how application of random forest models also indicated how specific welfares were not correlated to each other. Yeah? So, that's the other thing that came out. Uh, then, of course, you have the within the random forest model, as I mentioned, we took the same data, and through that we could identify. We ran the CRM model again, also for that same data. So one big thing that came out of this was the idea that you could use a random forest model as a precursor. What I mean by precursor is it helps you identify which well pairs are not related to each other. And once you know which well pairs are not related to each other, you can use that information and feed it back into the CRM models where you can predefine these Fij values to be zero for those well pairs because they are not related to each other, and that helps you reduce the size of the problem that you're trying to solve. Yeah. And of course, this is again another example. We're trying to optimize for a field here. Actually, this is in Germany, I believe, where it's an old reservoir again. You had over 150 wells that were drilled. Some of these early producers were converted to injectors. And here, and again, the power of data-driven models, where you were able to quickly identify a quick number of injector and producers that would be relevant. So in this case, 10 and 5. Um, and here, what I wanted to show in this slide is how these Fijs are used to interpret the relationship between injectors and producers. So let's say you ran the CRM model, you got these Fijs, right? I mentioned you optimize, you run a nonlinear optimization, you know how much you're producing, you know how much you're injecting. So through that equation, you can find out Fij. Um, And so these are your injectors. So the rows indicate injectors, the columns indicate the producers. So here you can quickly see that if you look at A4 and you look at all the FIJs and you do a sum total of all these FIJs, it's hardly zero point 0.1, right? Which means that whatever you're injecting in A4 is actually not going towards any producer. Uh, and through that you can come to the conclusion that A4 is actually an inefficient well for that matter. Yeah. Whereas when you look at A13 and A15, when you do a sum total, you're getting 40-50% here. You can see 30% is going to A10, over 15% A25, 10% to A27, and so forth. So at least whatever you're injecting is going towards somewhere, right? So that then helps you understand how A13 and A15 are actually efficient in terms of optimizing your reservoir. Yeah. Okay, so of course there are multiple verifications one could do to make sure. So these are results coming in from purely data. How do they compare with other approaches? So one other approach typically used is something called the streamline approach. So here you can see you can see more streamlines around A13 and A15 uh, as against A4, which has a lot less streamline, thereby showing that indeed was an inefficient well. So you can also verify some of these approaches by streamline approach. The next, we also wanted to showcase, how does it compare with the traditional reservoir simulation approach? So here you can see a comparison where the left is nothing but the oil production, the CRM model, the history associated with, and the prediction coming from the CRM model, as well as the actual history that was observed in the field, right? And on the right, you see predictions from the simulation, prediction from the CRM. And then, when you optimize it, when you say, how do I redistribute water so that I can get a higher oil recovery? This is the potential increase that you can get through the CRM model. So, you can see that the model is able to predict that. Yeah. So for this specific case, again, you could run these optimization scenarios where when the objective was to actually close down A4 completely. The idea was to reduce injection in A15 by zero point 0.7 times, and of course increase injection in A13 by 3 times. Now, it's possible that sometimes you can't really increase injection in these injectors. So essentially you add additional constraints accordingly and try to see what new values you can obtain really from these optimizations. So in summary, all these data-driven approaches allow you the flexibility to at least understand and build in some additional constraints that you have in the system. All right. So, we spoke about simple fields, but what happens when the field itself is complicated? So, let me talk about this specific example where you had a legacy field. Think of it like a mature field with over 100-year history. You're talking about over 800 wells with 400 injectors that are producing from actually 27 different producing layers. Yeah. So you have commingled production in there. So the goal was, is it possible to identify how much production was coming in from individual layers? Uh, can we determine connectivity between wells to determine list of effective and ineffective pairs? Um, and perhaps can we identify where we are recycling and perhaps even shut them down? Or are there opportunities where we can try to redistribute water amongst wells so that we can increase oil recovery without spending any capex? Yeah. So it turned out, it was indeed challenging because you're talking about a historical field, so over 60 years of data, uh, which had widely varying rates, right? And then of course, layer information was there, but then one had to really coordinate or collate from different sources, different models that they have. Reservoir model had some information. Their production model had some different information. So once you try and integrate all that information together, it becomes much more valuable then to run these data-driven modeling exercise. So the reason I've just listed out these challenges are it's not as straightforward to just run these data-driven models. There's a lot of work in trying to make sure that the data is consistent, and you really need to work as a team to put this information together, so you can really unleash then the power of these models directly. All right. So, what was the big advantage of trying to implement these models? Well, now you were able to actually obtain how much each layer was producing from each of these specific wells. Remember, I spoke about how the CRM models help you actually with the allocation problem and how they can be adapted to a multi-layered reservoir. You can now know how much is coming in from individual layer, and this is not actually possible in a reservoir simulation model, right? I mean, you're just simulating. You don't know what the individual contributions are, but here you are, because you're collecting data. You can go back and allocate, and through that determine which layers are effective, which layers are ineffective. Yeah. We could identify where they were just recycling water, so you could come up with a list of wells which needed to be shut down, right? And that itself is a huge savings, right? Because water also has some handling cost at the surface. And then you could go back and rerun an optimization saying that now that I know the FIJs, what should be the new injection, so that I can increase recovery, right? So we ran that, and now it's currently being implemented as we speak. And also, you could also plan for different scenarios. So if you have an oil price fluctuation, if there is a drop in oil prices, they could actually focus on reducing their operations cost. And one way to reduce the operation cost is to reduce water. So what are the avenues for them to actually reduce water without impacting too much of oil? So they could really identify which wells to kind of shut down selectively, or which injectors to shut down, so that they can reduce the net amount of water that they produce at the surface. All right. So this was again the application on water flood, and I just wanted to demonstrate how some of these data-driven models can be useful, uh, how they are integrated in some sense, and how solutions of these help you optimize essentially water flood operations. What I want to do next is speak about essentially hybrid models in the space of combining machine learning models as well as simulation models. Now, before I move further, are there any questions on this section?
Yeah, actually, I have a question regarding the feature selection where you used in the Egyptian field. Uh, you were selecting according to the Pearson coefficient of correlation, I believe. So, how do you like distinguish between if this specific injector is affecting this specific producer, or there are other wells that are affecting it, because you cannot really know if this injector is affecting or not, because there are other factors that taken into consideration at the same time.
That's a good question. So, what you do is you run it for all possible injector producer pairs. So, what we're talking about is, let's say you have three injectors and five producers, right? So I1 P1, I1 P2, I1 P3, all the way to P5. Similarly, I2 P1. So you run it all for all the possible pairs, and through all those pairs, you identify which ones are, related, which ones are not related. Okay. Now, obviously, you're right. There are other factors that would also influence. How do we know that it is just this injector that is contributing? So, one thing that we need to remember, this is a qualitative approach, right? So, at least you are able to then reduce, let's say, especially in this 800 well case, you can quickly narrow down to 20, 25 well pairs, which are relevant or which are not relevant. And of course, you need to dig into some kind of a secondary data. For this specific case, they had salinity data, which could further establish the relationship that indeed they were related. So you're right. So you first run it across all possible well pairs. B, you use some kind of a secondary data to further validate, because it's more of a qualitative approach. But the CRM model, on the other hand, is a more quantitative approach. So you get actual values, you get actual estimates, um, and the other aspect of running these data-driven models is to see what output you're getting in from different models, and see where you have maximum consistency in that respect.
Thank you.
Yeah. Any other question? Okay. Well, the other models that I want to talk about are again, for surveillance, and I will come on to. So, in summary, when we talk about surveillance, there is this qualitative and quantitative approaches. So, I spoke about cross correlation analysis, random forest model. So, here what we are doing is we are really identifying where the thief zones are, where the effective injector producer pairs are. right? And these are more qualitative in nature. The quantitative approaches are these capacitance resistance model, where you're looking at how much injector is lost, which wells and how much water to inject, especially in this region. Yeah, and I've just listed some of our publications in this area, and one way of combining them, which we do, is essentially you use the quantitative model of a random forest model. It actually tells you which well pairs are not related, and then the remaining wells, and we use that for solving the CRMP model. So that's the way we combine models in this space. All right. So let me change gears, move to reservoir management workflows. And typically when you're working in companies, this is the kind of workflow that folks follow. You start with a static model, right? The geologists, geophysicists, they create some kind of a static model, and then they get passed on to a reservoir engineer who then starts creating a dynamic model where you plan in wells, you simulate flow by running reservoir simulations, and through that you start making recovery predictions. So this is a very typical workflow that we follow in the industry. Now, depending on whether it's a greenfield or a brownfield scenario, you always have the static model, but then on the dynamic side, what you do is, let's say you're trying to find the location of a new well, right? And you had an existing field, you have some production, so you probably do some history match, and then you're trying to figure out where you should be placing the next well. Now, what is typically done there is, this is very manual in nature. So you keep playing around the well location. You run a simulation, you obtain some NPV, you go back, change the location, see what you get. And this happens back and forth. And, it goes back to my experience of, working in Shell, and, always kind of constrained by time. You have like a couple of weeks to figure out where the well location is. And you probably know that whatever you're picking is not going to be the optimum, because you really not scanned the entire solution space. Okay. um, and I was thinking this was just my problem, but as I spoke to all the other reservoir engineers, it turns out it's a common industry problem. We really don't know. So essentially, so this is where the idea began of, are there opportunities to really automate and reduce the time taken to scan the entire solution space, yeah, using machine learning algorithms. So typically, there is. So it turns out there is, and what we do is we do that by creation of these hybrid model approach. So what I have on this slide is just a comparison of how it's typically done right now. So we do a sequential approach. We make some manual changes. We wait for simulation results. Obviously, it's time consuming. And as I said, even if you think you have the optimum, you don't really know, because you've not scanned the entire solution space. You're restricted by time aspect there, if you will. Whereas the other approach that we've kind of brought forth is what is called the hybrid model, the creation of a hybrid model, where you start with actually a single file, single simulation file, and what this does is it generates a hybrid model, and through that it shows effectively productivity map of your entire reservoir simulator. Yeah, and the trick there is we use something called fast match model in addition to reservoir simulation model. So once you have a single reservoir simulation file, we run some random simulations, we feed it into a gradient booster algorithm, and then we also run what is called fast match model and feed that also to the gradient booster algorithm, and through that generate productivity map. So it turns out when you have that gradient booster algorithm, it's much more predictive, because you're also feeding in results of the fast match model, which helps capture some of the physics associated with it. Yeah. So fast match model, was introduced actually recently, but it's been around for a while. So essentially, think of it like the simple pressure equation that you're solving. So let's say you had some wells that you placed at this location. So what you're trying to do is you're asking a fluid to actually flow, and you're finding the fastest path that it can take in a particular time. So we refer to these as time of flight calculations. And through these time of flight calculation, you estimate drainage area for a specific well location. Yeah. So effectively, as you can see, if I place my well in these three locations, if you see the last graph on the right, you can actually compute the drainage area around that specific well for a particular time period. So effectively, and that captures a lot of stuff, right? It captures the permeability, um, it captures the viscosity, it captures the compressibility as well as the porosity associated with. So think of the fast march model as some kind of an averaging around your entire reservoir. So effectively, what we do is you vary the well location. You run a reservoir simulation, you feed that to machine learning, but you also run fast match model for that location, and you also feed that to the machine learning model. And that is what makes the machine learning model more predictive in nature. Yeah. So just want to demonstrate that for one of the brownfield case studies. This is, of course, the non-field, which is publicly available. So let's think about the non-field. Let's assume that it had 6 wells. Where we had 3 injectors, 3 producers. It's shown here, and our goal is, this is of course a complicated field. I have over 300,000 grid blocks. You start with a single Eclipse simulation file with all inputs, and the goal is, where do you place a new infill producer well? Let's say you're tasked with knowing, where do I place the next producer well. The question is, can these hybrid models help develop the location of the new well? Well, it turns out it can. So this is how it works. So here you see the existing wells. The circles are the existing producers. The triangles are the existing uh, injectors. What each of these blue circles represent are the random reservoir simulations that we would run, right? So what this particular model does is it takes in every single dot or every single blue circle, creates a new simulation file for it, runs the simulation. The input is the location of the well, right? The output is the actual reservoir simulation output. You feed both of these to a gradient booster algorithm. Similarly, for that location, you also run the fast match, so you estimate essentially the drainage volume around that specific location, and you also feed that, and through that you generate what I call um, essentially the hybrid model, right? And once you have a hybrid model, you can then extrapolate it to your entire reservoir. So here on the left, you see a productivity map generated from your hybrid model just by using 150 simulations. On the right, what you see is the same NPV map being generated by running reservoir simulation at each of these individual points. Yeah. So what you can see is the darker red regions are the regions which you probably want to drill your next well, because these are higher NPV values, right? And when you do a comparison, you can see that they are actually strikingly similar to each other. So in summary, hybrid models can be really predictive, and they really require just a fraction of reservoir simulation, all of which can be automated in some sense, because as I said, you just start with a single reservoir simulation model, and all this work is happening in the backend. Yeah. So in some sense, so this was an example of trying to showcase how infill drilling location can be identified through dramatic reduction, right, in decision making time. So the way some of our clients are using is, you can just simply upload one single simulation file in the evening, come back the next day, and you can know which areas to possibly place that specific well. Of course, how do you, obviously there are so many locations. How do you globally optimize it? So we've also coupled it with a global optimizer. So let's say they are also extendable to a greenfield case. Let's say, you're trying to develop a reservoir and you have, say, 5 wells, but you don't know where to place those 5 wells. So essentially, we do a similar approach here. You generate a hybrid model. Through that, you generate potential locations of those 5 wells, and then we integrate it with a global optimizer. So we use a global particle swarm optimizer, and through that you can actually get to know the exact optimum value, or rather the well locations of these specific wells. So again, here starting again with a single reservoir simulation file, you're using this combination of simulations and fast match model, feeding it into a machine learning model, in this specific case a gradient booster algorithm, which helps extrapolate it for your entire reservoir. And of course, these models can be combined with global optimization algorithm, which help you optimize well location. So essentially, companies can reduce their time that it takes to really solve this well placement problem. All right, so just a summary of these hybrid models. So, here, at least in this context, it helps dramatically reduce decision-making times through automation of simulation runs. And, I would say the secret sauce here is nothing but the fast match model, which helps make these models more predictive in nature. If you were to do that only with random simulation runs, you wouldn't get these predictive models. And of course, you have much more confidence in solutions because you know the training scores, you know the testing scores coming out of these models. Now, in addition to well locations, we also integrate well controls, right? It can also be integrated in this framework. So not just where to drill, but essentially how much bottom hole pressure to maintain to produce, or if you're injecting, what should be the injection rate. So all those can be effectively obtained through this approach. And then also coupling with global optimization problem can really lead to comparatively quicker runs. Now, traditionally, what happens is you kind of couple these optimization algorithm to reservoir simulation. So, and that coupling, because each of that would require a new simulation run. Simulation run is expensive, so you're talking about a lot more time that it would require in order to run these models. But when you establish that coupling with hybrid models, these can be relatively faster, and also you can do much more runs because it helps you, and through that effectively distinguish between a global and local minima in that respect. So this presents a new phase where we are trying to integrate with existing tools, existing reservoir simulation files, or existing toolkits that folks have. And in some sense, this is the new wave of expertise in a box solutions that we are trying to build, and it really represents a disruption in typical linear workflows that we are so used to in field development planning. So as the world moves, the oil and gas industry moves, we expect to be more embrace of such solutions where we're focusing more on automation so that we can focus on arriving at decisions much quicker and faster for that matter. All right, so this is an overall summary of my talk. I mean, I started by listing out specific models, right? I mean, I spoke about analytics, some machine learning models, reduced physics and simulations, and what differences there are between them. I spoke about a few cases. We have actually implemented some of these for some fields. Um, and then we are actively working with some companies, especially in the space of greenfield and brownfield optimization, where we are combining reservoir simulation with these hybrid models that can really disrupt a lot of these linear modeling workflows. So, and these are some list of publications. We come from the academic background. I was a faculty in University of Oklahoma for a few years before starting their mine. So obviously, we publish a lot of work that we do. So, essentially, if you're further interested, these are some of the resources that you should definitely get a hang with. Uh, and also, there are some learning resources. I do realize I'm speaking to a student community here, so not everyone is essentially well versed with some of these techniques. We do conduct training courses. I mean, I personally do the SPE training, and I think there might be one at this year's SPATCE. But there are some free resources too. So there are some online courses, some books that are available. I've listed some useful blog here. So what I'll do is I'll probably circulate this to Habib, and we can share it with the broader team. um, and finally, yeah, I just wanted to thank the student chapter for hosting me. We are also grateful to our user community and our, as a startup, you're always grateful for the initial guys. Um, and actually, about a startup, well, it turns out uh, we are lucky to have folks who have at least two of the three skills that I have listed there. I gave an introduction about myself. A lot of my contributions have been in the space of improved recovery and high fidelity algorithms specifically. And as I said, the platform has been deployed. We work with several companies, and we published a few papers as we work, and I've just listed them. And yeah, with that, like to end my talk and happy to take any questions.
Thank you so much, Ashwin, for the presentation. It was really fruitful. So I have a question. How does the algorithm that uses only single simulation works? Like generally, when we build the proxy models, we need the sensitivity analysis in order to cover a range of data that when we use them, we're using the ANN or a supervised learning algorithm. We can have an estimation about the output, a prediction for the wide range of inputs. But if we have one model, we don't have that much data. So how does the hybrid model works?
Yeah. So, in that case, and, typically you don't have just one model, right? I mean, you will have multiple models. So just as an example, you might have a P10 case, a P90 case, a P50 case, right? So essentially what we do is we create hybrid models for each of those cases. And we run optimization on hybrid model for each of those cases and identify the common points across it. In order to finally predict which is the optimum. I didn't go over those details, but you're right. You essentially you need to have that. And what we typically do is we create a hybrid model, and we have internal algorithms which help you identify the common well location amongst all possible cases.
What about the global optimization? When you use the global optimization, the particle swarm algorithm you talked about, why do you use like the particle swarm algorithm and you don't use other algorithms like the gray wolf or the genetic algorithm?
Oh, one can actually use other algorithms. Well, we just are more comfortable with it. I mean, to be honest, it's just a matter of choice. Actually, I don't have anything against the other algorithms, but it doesn't matter what algorithm you use. At the end of the day, you should be able to know whether it's global or local minima, right? And at least for this case. Once you couple it to a hybrid algorithm, you can run more particle swarms, meaning you can have different starting points and actually go back and check if you're reaching the same optimum, meaning the global optima, right? If not, you would be reaching a lot of local minima. And because you couple it to a hybrid model, you're able to run as many swarms, thereby increasing your confidence in differentiating between local and global minima.
I have used the gray wolf algorithm. I think that it is really good in terms of finding the global optimum because like this algorithm is more precise. Like I compared it in one case and I found that it gives more precise results, like with a small increase, but small increase in oil industry is like big increase in profit. So I think maybe given that the try can generate better result. I don't really cannot really tell about this problem, but for my problem, it gave a better result because like it's more of a new algorithm in 2014. It was released.
What
So
is the
yeah, I
name?
think
What is the name of the algorithm?
Gray Wolf algorithm.
Okay. Okay.
Yeah.
Interesting. Yeah. Sure. We kind of went in for some methods which were established, which folks had used before. But yeah, whatever works, to be honest, I mean, whatever works. But the ability is to go back and cross check to see if it really works. Any other questions, folks?
Do you have any other questions from the audience?
Questions or comments for that matter? Any thoughts? Are you guys doing some of this research?
This is Muna, the communication outreach person for the SB. I don't have a question, but a comment actually. So I'd like to thank you for your time, for your support, and the great presentation. It's a very fruitful one. So we are happy and pleased to have you among us, and we hope to have you next time.
Sure, absolutely. Yeah, I think I spoke a lot of stuff. As you guys enter the workforce, I think it's critical that we embrace new tools and new technology, and you guys are going to make it happen. So, yeah.
Thank you so much. I really appreciate your time. So I think we should stop the recording.